Okay, here we go. So this week we are talking about this is week number 7 in the workshop practices course. This week we are talking about the CSA Z434 standard for robot safeguarding. So what does that mean exactly? Z434 is a standard that we use to basically applies to any type of machine that has a robot involved with it. So this lesson is going to be kind of an overview of the standard and all the individual components of it. We're not going to get too deep into it, except for 2 specific calculations that we will do. I'll show you how to do those. One involves stop time, and one involves basically height and distance of fences involved in with a robot type hazard. Okay, so we'll go through all the different sections of the standard here. Just give kind of a brief overview of what they mean. The standard is quite lengthy when you get into it, but a lot of this will seem kind of familiar to you from things that you've already learned in this course. So, section number 1. Back up here. Section 1 deals with the scope that the standard would apply to. So this applies to the manufacture, remanufacture, rebuild, installation, safeguarding, and maintenance, repair, startup, training for industrial robots or robot systems. So important things here: manufacture, remanufacture, rebuild. This applies to any basically new equipment. So think about that. This is essentially new or modified equipment. So if you have a robot system in a plant right now that was installed 30 years ago, it does not need to comply with this standard. Things don't need to be updated as standards change, but if you do work on something, or if something is new, or if you do modification to it, then when you do those modifications, you need to make sure that they are held up to whatever the current standard is. Okay, so you don't need to go back and change things as standards change, but if you modify equipment, those modifications and your entire system needs to conform to whatever the current standard is. So keep that in mind. And its purpose is to enhance safety of personnel associated with the use of robots or robot systems. The applications is covered under section 2. Anything that is new, used, or redeployed are covered. Like I said before, does not apply to things that were installed before the standard is released. As long as they are guarded, so that any intrusion into the restricted space causes a stoppage of automatic cycle. So basically we're talking about guarding around robot cells, and have compliant e-stop circuitry. Okay. Section 3 talks about some definitions. So envelope, the envelope of a robot, a 3-dimensional volume of space encompassing movement of all parts of the robot. So if we look at this robot right here, what we talk about as working envelope, we're basically talking about anywhere that it is capable of reaching. Okay, so if it is capable of reaching a space, that is within its working envelope. An industrial robot, by definition, is something that is automatically controlled, reprogrammable, multi-purpose, and has at least 3 or more axes. Okay, so 3-axis, auto-controlled, reprogrammable, multi-purpose, that defines an industrial robot. Industrial robot system is basically including all of the hardware, software, power supply, end effector, any other machinery or equipment in the safeguarded area. Okay, so that's all the associated equipment with the robot. Section 5 of the standard deals with performance requirements. So any guards that you put in place around around a robot. So we have a robot system here. And we're going to put a fence around this. Any of this fencing must be built to withstand operational forces. So basically, you can't build this fence out of tinfoil. Okay? It must be made out of some type of industrial material that is built to withstand the operational forces of what you're doing with it. Okay? Mechanical devices shall have a physical link between energy source and interlock mechanism. So if you have a door here, and we're putting a door switch on this door, okay, we talked about safety gate switches or door switches. If we are putting a door switch on this door here, that must be interlocked to shut down this robot if that door is open. Okay, that's what we're talking about here. So a physical link between energy source and interlock mechanism. And electrical devices upon failure shall not allow operation to continue upon failure. Now we have a word for that we have learned. We call this fail safe. Alright? Upon failure shall not allow operation to continue. Alright? Fail safe. So all of our devices we use must be fail safe. If they fail, they're going to shut things down. More performance requirements. Light curtains, area scanners, interlock, safety mats, two-hand controls shall all be independently certified by their own standards. Provide a means to readily observe if they are operational. So for example, these light curtains you see here, you can't see the little red beams that go between the light curtains, but what you will see on a light curtain, they've got these little green lights here, okay, that show if those green lights are on, that means this light curtain is actually operational. Okay, so you should be able to tell that these safety devices are working because they should light up in some way or somehow indicate that they are operating. They must not be affected by the environment they are intended to be used in. So if you are using a light curtain in a weld cell, this must be, if this is being used in a weld cell, it must be rated to be used in a weld cell. Okay, so it must be weld rated. That means that the electromagnetic fields generated by welding will not interfere or damage the light curtains. Okay, they must be, if you're using this in a washdown area, these must be devices that are capable of a washdown environment, that they're not going to fail if they get sprayed by water or whatever. Okay, they must conform to whatever environment they're being used in. The installation of these devices have to be done according to the manufacturer's specifications. Controls shall be located outside of the cell. So if you have a robot cell, controls for things should be located out here. They should not be located in there. Okay? Should be outside of the cell. So if you need to maintain things, you don't need to go inside the cell to get to them. They should protect against inadvertent operation. Robot e-stop shall override all other controls. E-stop shall stop all other hazards. So if you have an e-stop button over here and you press this, that should shut down the robot. It should shut down the conveyor going into it and the conveyor going out. Okay, there shouldn't be any question of what an e-stop does. It should just shut down everything within that area. And things should be well labeled, and the lighting should be good in the area as well. Personnel, it is the responsibility of everyone at every stage of the process to conform to these standards. Section 8 talks about prescribed methods. Section 9 talks about performing a risk assessment. And we've already covered that in this course, so that is actually part of this. How to do a risk assessment is part of this standard. Section 10 talks about the implementation. Your safety-related control system shall be designed to withstand Operating stresses, like you said before, it must be made of good materials. The influence of the processed materials, so again, depending on your environment. And external influences, so it must be rated to stand up to the environment you plan on using it in. So if it's in a welding area, it must be weld rated, must be able to stand up to that type of environment, or a washdown area, or any type of harsh industrial environment like that. It must be capable of living up to those standards. Safeguarding device purposes. They should prevent access, cause hazard to cease before access, and prevent unintended operation. So if you have a cell like this, you should have something like a light curtain here that prevents access. That's what that's saying. Cease operation before you're in there. It should contain parts and tooling, such as projectiles or other processes like noise or laser light, should also be contained as well. An example of that, this is a welding cell here. So you can see lots of things going on in here. You'll see the stuff on the fence here to contain the light. Okay, that's a good example of containment. We want to be able to contain all that sparks and light and things like that. That's another thing we need to consider. And then we're going to get into the calculations that we're going to do for this one here. This first one here, this is our stop time calculation. So this is safe distance. Now we have this formula right here. Switch. So this formula right here, this says ds is equal to k times ts plus tc plus tr plus dpf. So ds, that means safe distance. Now when we say safe distance, we mean we have a hazard here. I'll call that a hazard. And then we're going to put a light curtain right here. We have a light curtain here. We have a person out here. So the question is, this distance right here, how far should that distance be? How far should that light curtain be mounted from the hazard to ensure that if that person walks through the light curtain, we can make sure that that hazard has come to a complete stop before the person is capable of reaching it. Okay? So let's think of a spinning saw blade. And you have a light curtain here. And this guy wants to stick his hand in here and grab that spinning saw blade. How far does this safety device have to be mounted from there to ensure that he cannot do that? Okay, so there's a couple factors we need to consider in order to get that distance. So the first one is, how fast can this guy move his arm? All right, so we actually have a value for that. This has been determined by safety people, we'll say. And this value is what we're going to call K, the speed constant. And that is 1.6 meters per second, or 1600 millimeters per second. Okay, so K equals 1.6 meters per second. That is how fast this guy could reach his arm. So doing that, or walking or whatever, that is how fast a person is capable of moving. Okay, so that will give us the time. So now we have a distance, we have a time, or we know how fast this person can travel. How long does it take for this hazard to come to a safe state? So in the case of this, how long does it take for this saw blade to actually stop? So there's three factors we need to consider in order to get that total amount of time. So this is what we're adding together here. 3 times we're going to add together. The first one is the stopping time of the machine. TS is stop time of the machine. So that is how long does this saw blade take to stop as soon as we command it to stop. Okay, that is the definition of that one. So let's assume that we have, I'll drop here now. That's our saw blade. And this goes to a motor that runs that. This motor is run by, let's call it a PLC. And this PLC is connected to a light curtain. Let's say those are all our factors that are involved here. So basically, as soon as we tell this motor to stop, this has some physical time for actually it to stop. This is the longest of these 3 times. And that one is called TS. Okay? So between the time that our motor actually cuts out to the time that this thing comes to a complete stop, that is TS. This next one here, TC, stop time of the control system. So that is the time that it takes between the time that we tell this PLC to stop, that it takes for us to read those inputs, process those inputs, and give an output that gives a stop command. That is called TC. And that is dependent on how fast is our PLC. So that's going to be a very small time, but we still need to factor that in there. And then the final one, so that's basically processing time of the PLC. The final one we're going to consider is going to be this one here, TR, which is the response time of the safeguarding devices. And this is this one here. And that is basically how long does it take between the time that I put my arm through this light curtain, for that light curtain to realize that I put my arm through it, and to give an output to the PLC. Okay, that is TR. So when we take this time delay, plus this time delay, plus this time delay, add those all together, that's going to give us a total amount of time. If I take that time and multiply it by 1.6 meters per second, that is going to give us a distance that I am capable of traveling between the time when I break this light curtain and the time when this, so the time when I break that light curtain to the time when I actually, when this actually comes to a complete stop. How far can I travel in that distance? And then my DS should be just greater than that, and that will guarantee that I cannot reach this in time. Okay? So that is what this calculation is. Now the one other factor in here, we're going to add one more little factor in here that's called DPF, which is called the depth penetration factor. Now, depth penetration factor is basically how far can you put your hand through this light curtain, or any part of your body through this light curtain, before it even realizes that you've put something through the light curtain. Now what that is dependent upon is the spacing of these beams. So if you have your finger, if you want to think of your hand as being kind of wedge shaped, and this is the beams of the light curtain. Looking at this from the side now. You might be able to get your hand so let's say you can get your hand or your one finger through here. You can get that far through before you actually break these beams. Okay, so how far is that? This is what we're calling DPF. Okay, how far can you stick a finger between the beams of this before it even realizes that you've done it? Okay, now this is dependent on the OS, which is optical spacing, optical sensitivity of the light curtain, which is basically how far apart are these beams. Okay, now if we know that, we can calculate it. Because we're going to basically say OS minus 3.875 millimeters multiplied by this will give us our DPF. Now how do we know that OS? That is actually a number that you can find in the specifications of light curtains. They will refer to it as the resolution. So for example, these light curtains here, these come in two different types. This one's I'm looking at here. You'll see that there is a 14 millimeter and a 30 millimeter spacing. And this is what we call finger resolution versus hand resolution. So 14 millimeter is finger, 30 millimeter is hand. Okay, so 14 millimeters or 30 millimeters. So let's look at a calculation here as an example. So let's say I have a stop time of 0.5 seconds, a controller, a TC of this, and a TR of this. So what was the first one? TS, TC, and TR. Let's say OS equals 14 millimeters. Okay. If we take all those things and calculate them out, then I think you will get, I think, 264.225 millimeters. So this is basically saying this is my hazard, this is my light curtain. With these numbers, I can travel 264 millimeters before this hazard comes to a complete stop. So I would need to put this light curtain at least it would need to be at least 264 millimeters from the hazard. Okay, so that is how we do the safe distance calculation. Okay, so section 11 deals with some other requirements. Design and construct to prevent any part of the body from reaching. So you need to protect your fences. You need to protect your perimeter guarding so that someone can't go around, under, through, or over them. Must keep inspection and maintenance records. Section 13 deals with startup. Section 14 deals with training. And when we talk about going around and over, we have some things where we talk about reach over hazards. And we are going to do a calculation for this as well. So we have a hazard. Okay, a hazard has a height defined as A. So a height of the hazard. We have a fence that has a height as well. So the height of our fence. And we have a distance between the fence and the hazard. A different color here so you can see it better. The distance between the hazard and the fence, height of the hazard, height of the fence. Those are our three factors. So because this guy here can reach in an arc, imagine he's got his shoulder here, he can basically reach in a sweeping arc here. You want him to not be able to touch this hazard. Okay? So the taller the hazard is, the further this needs to be away from the fence. Or the taller the fence is, the closer you are allowed to actually bring the hazard to it because it impedes his ability to reach over it. Okay? The shorter the fence is, the further away the hazard needs to be. Okay, and we actually have a chart that helps us figure this out. It looks like this, where we can look up our height of the hazard here. So find your height over here. And you have your height of your fence along here. And then you can cross two values here and find a value here that says this is what your minimum safe distance from the hazard must be. Okay, so let's do an example of this. A hazard is 1.2 meters tall and is behind a fence 1.4 meters tall. This is our hazard. This is 1.2. This is 1.4. Okay. We want to find what is this distance here that ensures that he cannot reach that hazard. So our hazard is 1.2 or 1200 millimeters. Our fence is 1.4 or 1400 millimeters. So 1100 that would be the minimum distance that we're allowed to put there. Okay, so that hazard must be at least 1.1 meters away from the fence. Okay, that is how we solve problems using this chart. All right, so we are now going to do a couple of practice problems involving each of those two equations, and these two calculations are the kind of the two important takeaways from this standard. Okay, so this is the Z434 standard.